coursework page. Okay, so work done and energy is our topic for the next 2 days. So we only technically have 2 classes left, like including today's class, so that time-wise we are very, very crushed, right? Okay, so now energy is the ability to do work, and work in physics means something different than work in like everyday English. Okay, so energy is the ability to work. So work in physics means the amount of energy that you spend into doing something. So now energy is a lot like money. Energy is a lot like money. So energy is a scalar quantity. That means you don't need direction. Just like money, right? You don't have to say, I have $30 facing south. And it's measured in joules, which we already kind of used that unit in our previous chapter, right? On the circuit chapter. So energy is measured in joules. Okay, so work, which is the first thing that we'll do, is a change in energy. So when you change the amount of energy in an object, so if you give an object energy, you are doing work on it, right? So that's what work means. So we have a basic definition for work. Work is change in energy. So, for example, you make something go faster. You're giving it energy, then you're doing work. Or you pick up your backpack and you move it to a higher location, you're also doing work. So whenever you're trying to, change an object's speed or change its height, you're doing work to it. So in order to, give an object energy, the easiest way to do this is by pushing the object. So the amount of energy that you spend by pushing an object depends on 2 things. So we call it work done on the object. It depends on 2 things. Depends on, number 1, how much is the force that's actually pushing the object. Therefore, there you get a pi force, right? So of you pushing something. And then the object also moves at a certain distance. So let's say you push a box and the box eventually moves over, let's say like here. Okay, the box eventually moves over here. So let's say you push the box from here to here. There you go. That is a distance, okay, which is measured in meter. So if you know the force that you use to push the object in Newton and the distance the object actually moved in meter, then the amount of energy that you spend, which is called work done, on the object is equal to just the products between those 2, which is the force that you use to push the object. So it's the product between force and distance, okay, and the distance that the object traveled. Now, one thing that you need to be careful about is the force and the distance have to be parallel to each other. So like in this case, the force and the distance is parallel. Parallel doesn't mean the same. Parallel can also be opposite, but they have to be kind of in the same direction or opposite, not perpendicular. So this is parallel. Okay, so your force equation, your force direction and your distance direction has to be parallel to each other. Okay, so now that's the equation that you see on your formula sheet as one of the first one on energy. So the amount of energy that you input to the object is equal to the force multiplied by distance. So your force multiplied by the distance that the object is traveling. So pretty easy to do. It's a two-part equation, right? So not that bad. Now in physics, you usually talk about the work being done on an object. So how much energy are you putting on an object or removing from an object? So if you hold a 30 kilogram weight at a height of 1.5 meter, you're using energy. However, the work is not being done on the object. The work is being done, now think about it. Did you change the energy level of the object when you're just holding it? So let's say you're just holding like a box in here, like standing. Okay, just holding a box. You're not picking up the box, but you're just holding it. Right? So you're just holding a box. Now, holding something actually doesn't add energy to the object. Picking it up does. Throwing an object adds energy to it. But just holding it, for example, I mean, think about it. You can be totally unconscious and then lying on the ground, and I just put a box on you. Well, obviously, you're unconscious, you're not spending any energy, right? But see, the box is still holding on your body. So holding something doesn't add energy to the object. Now, you can pick it up, that will add energy to the object, or you can throw something, flowing something from one point to another, adds energy to the object. So therefore, holding something has a work done of 0. There's 0 energy transfer between you and the object. You have to pick up something or throw something in order for work to be done. So you're not transferring your energy into the box by just holding it. You're just holding it there. Now think of it like this. Although you are exerting a force, so technically speaking, right? Think about it. So when you're holding a box, which direction is the force that you apply? This way, right? You apply a force that goes upward, which is technically the normal force when you think about it, if you're holding a box. But did it move? If you're holding the object, the distance moved is 0, like the object is not moving. Therefore, no work is done. Okay, so no energy transfer to an object if you're not moving it. So then you can think about it like this. So if I pick up this thing, yes, I'm doing work because I'm changing distance, right? I'm changing height. So my force goes that way, the distance also goes that way, so there is a work done. Now, however, if I am pushing a wall, just like that, so I'm applying a force, but the wall is not moving. So then in the equation, yep, there is a force, but no, there's no movement because the wall is too heavy. I can't even make it move. So how much energy have I transferred to the wall? 0. I did not transfer energy to the wall because the wall did not move. So in order for you to transfer energy from one object to another, you actually have to make it move. So holding something is not making it move, so that is not transferring energy to it. Throwing something is making it move, so it's transferring energy to it. Picking up something also makes it move, therefore also we are transferring energy into it. So for example, lifting something up, right, as we were saying earlier, does require energy transfer. For example, now this is not holding a box, but instead someone picking up a box. So the box went from here to, let's say, here, right? So someone actually picks it up from the ground to a height of 1.5 meters. So this is the distance that the box actually moved. How much work is done on it? Okay, so you have to think about it this way. Think about dynamics, right? In order to pick up this box, how much applied force do I lead? How much applied force do I lead to actually pick up a box? Well, according to Newton's first law, that applied force must be at least balancing gravity, right? Its weight. Now, of course, can it be stronger than gravity? Sure, you will go up even faster. But how can it be weaker than gravity? No. If your applied force is weaker than gravity, the box won't even start moving upward. So you have to be at least matching gravity, right? So these two forces should be at least the same. So the applied force to lift something, right, is at least Fg. So the amount of applied force that you lead to lift up something is at least Fg. Now, it can be more than Fg, but at least, right? Therefore, we say, okay, so that's our applied force. Now, to calculate work done, so how much is the applied force? So we say, all right, then it should be the applied force multiplied by the distance, but our applied force is just at least Fg. And how do you get Fg? Mg. So what is the mass of the object? 30 kilogram. Then what is the force of gravity on it, or its weight? Its weight is going to be 294. So this is 294 Newton. So how strong should your applied force be? At least 294 Newton or more. So let's say we have the minimum amount, which is 294 Newton. And how much did it move? 1.5 meter. So force times distance, if you give you then 441 joules. So That means lifting up this box, you wasted 400-ish joules of energy from your body. Now remember, energy is like money. There is a certain amount in your body. You will have to eat and rest to replenish it. And that's why you get tired. If you continuously have to move this box up and down, up and down, up and down, you eventually get really tired, right? Because eventually you run out of energy, right? You eventually run out of energy. Remember, energy is like voltage in our last unit, right? So these are pisa. So every time you need to move that box up, you have to spend like 441 pisa. Think about it. And there's only a certain amount in your body. Your body is like a giant reservoir. You have energy in it, millions and millions of joules, but eventually it will run out. So that's what happens when you do exercise and then at the end you are tired. Okay, so now because of this, because when you're lifting an object up, technically you just have to work against gravity. So it might be a good idea to just combine those two equations together, because if apply force right here is just going to match gravity, why don't we just put the mg in the equation instead? So that is, of course, possible. So we say, well, I mean, if the apply force is going to be mg anyways, and the distance, so we call the distance change in height. So instead of d, we call change in height. Because sometimes you are, so change in height. Okay, so where m, of course, is the mass, and g is the, well, acceleration due to gravity. On Earth, if you're on Earth, that number is 9.8. But if it's not, then, obviously it's different, right? Okay, so now why do we have a change in height in here? Because you have to look at where is 0 for you. Sometimes, maybe you're picking up something from the ground, so whatever height you have is that change in height. Sometimes you might be picking up a book from the table, so the change in height might be, so for example, what if you have like a table and the object is actually on the table, and then you come in and you just pick up the object and you put it up here. So what is the change in height? You don't have to measure it from the ground. You measure it from the location of the box before it moved and the location of the box after it moves. Make sure that it's measured in meter. Then it's okay. That is for lifting up an object. Okay, so as long as you're lifting up an object, that will work. Now, but sometimes you're not lifting up an object. Sometimes you're actually pushing an object. So when you're pushing an object, then you just find out the pushing force and the distance that the object traveled. So for example, in this next thing, we are pushing a pumpkin. So a pumpkin is going at travels for 5 meters at constant velocity. Oh, remember in dynamics, right? Constant velocity means all the forces balance out. So no force is winning. There is a horizontal force of 3 Newton. How much work is done pushing the pumpkin? Okay, so we have this pumpkin in here, and it's on the ground. I mean, obviously. Then it has gravity, but then gravity is usually balanced out by normal force in our dynamic chapter, so these two doesn't count. Then we have someone pushing, from behind, right there, and that person has a force, apply force of 3 Newton. Now, the fact that it says the box is going at constant velocity means something is trying to fight that 3 Newton, and that will be friction, of course, right? So, I mean, otherwise, no one is fighting apply force. So, therefore, that means there is friction. And friction will also be 3 Newton. Okay, so now there are a lot of forces in here. So, which one are we using in order to do our work done? Well, okay, which one is actually provided by the man or the woman? Fa, right? No, the other forces are not applied by the man. Like the force of gravity due to Earth, normal force due to electron repelling, friction due to the surface rubbing against each other on the ground. So there's only one force that's actually directly responsible by the person pushing, which is this guy right here. And the box moved 5 meters, so we also know that it moves 5 meters. So distance is also there for me. Well, there we go. So the work done, how much energy did that person spend is apply force multiplied by distance. which is 3 Newton, multiplied by 5 meter, which is extremely easy, is 15 joules. So he wasted 15 joules of energy in order to push that box. So when you're doing this, make sure you're using the applied force, not the net force. Because technically speaking, the net force is 0. But we don't care. I mean, you have to tell me that that person right there is actually spending energy, right? He's pushing a box. I mean, after like 5 hours, he will pass out because he runs out of energy. So you know that he is spending energy. So you can't say, well, just because the net force is 0, his work done is 0. No, he's doing work. He's continuously pushing a box against gravity, against friction. So eventually he will tire out. So the energy is going to disappear from his body bit by bit. And then you need to rest and eat to get the level up again, right? Your body's like a rechargeable battery. It has energy. You can use it to do something, do some work. But then once it gets really low, you have to sleep and eat. It recharges, and then you can do it again. Okay, now this is a trick question. Takes like 5 seconds to do on a multiple choice. Someone is holding a pineapple. How much work is done? 0. Someone is holding a pineapple. Holding something does not mean work is done on it, remember. So that's a pineapple. I don't know how to draw a pineapple. There you go, right? That's good. Pretty good, right? And then just some, there, pineapple. Pineapple for you. So what is the work done? 0. Why is it 0? Because, well, you can think about it in the equation form. Because it's force times distance. Yes, how much force do you need to apply? At least gravity, we know that, right? At least gravity. So now we also, actually, remember, we have the other equation, right? mg, change in height. We can use that one too. And you can see, yeah, there is a mass. Yes, there is gravity, but you didn't change any height, right? The pineapple is not moving. You're holding it up. Holding it means, now you might say, Mr. Chang, don't you have to pick it up before you can hold it? Didn't you spend work doing that? Well, no. I can give you the pineapple. I do work. You just hold it. Right? You can just stay there and stick your hand out like this, and then I come in with a pineapple and I say, there you go. Right? So who is picking up the pineapple? I am. So are you doing work? No, you're not. I did work. You didn't do work. So you have to think about it like this. Holding something because you don't know who actually picked it up. During the time that someone's just holding like an object, there's no work done. Okay? So no distance means no work. The pineapple is not moving. Someone moved it, I agree, but not you. Someone did move it. Okay. Now we do have one, okay, so this one first before the one on the left, which is in different order. Okay, so this one is going to be slightly more complicated because we are combining kinematic dynamics and energy together. Woo! Okay, so first of all, I look at this. There's a car. There's a mass right there for you. And traveling at 61 km per hour is brought to a stop. Oh, this is V final. Not only that it's V final, it's a V final that's annoying because it's in km per hour. So immediately we go, ew, and then change it to 16.94 meter per second by dividing 3.6, right? So we have to get km per hour into meter per second before you can do anything. Now, stop in physics always mean, this is V initial. That's the first speed right there. Now, the final speed is 0 though. How do I know that? Stop. The car stopped, right? So V final is 0. So I know these numbers. Oh, that's also a distance travel for us. There you go. D is that. What is the work done on the car by friction? Okay, now, we don't have a person pushing this time. We have friction pushing this time. Okay, but I think in order to do this, I will actually need to find out the force of friction so that I can do work done by friction. However, how do I do force by friction? I will let you do acceleration first. I have V initial, V final, and displacement, so friction shouldn't actually be too hard. So let's do it. So we have all the numbers up here. So which equation help? I don't have a time, so do the V final square, V initial square plus 2AD. There's no time on that one. Good, perfect. We want one that has no time on it. 0 is equal to 16, I'm just going to write 17, plus 2 times the acceleration, which is what we don't know, times distance, which we do know is 42. Okay, so 2 times A times 42. Now, at this stage, right, I mean, this is our first chapter's work. I'm going to assume that you can do this on your own. So it's negative 3.42 meter per second square. So that's our acceleration. Good. Okay, so with acceleration, I can get forces. So let's look at the free body diagram on the car. Well, I have gravity, but that gravity should have been cancelled out by normal force. So I don't think I need to count that. And then we have one final force on this, which is friction. Now, friction is the only force on it, though. Why is there no applied force? Because this car is trying to brake. Just like when most of you are learning how to drive right now, you know that when you put your foot on the gas cars go forward. That's applied force. When you put your foot on the brake, the cars slow down, right? That is the braking force. So if you try to brake, is your foot on the gas? No, your foot is on the brake, right? If your foot is on the brake, then the only force in your car right now is friction. There is no applied force anymore because you took your foot off the gas. I mean, in order to stop the car, you kind of have to, right? It's not something you can choose. So therefore, the only force left in here, in this picture, if I ask you what is the net force, you then tell me, well, Mr. Chung, net force is just friction because no other forces can survive. The gravity cancel with normal force. Applied force doesn't exist because you're no longer trying to go forward. You're actually trying to brake and slow down. And we have acceleration. F net always equal to ma. Always. Still true. So friction is just ma. Mass of the car is heavy. Acceleration is negative 3.42. And I have my friction. There we go. Okay, so friction, the force, is roughly negative 4,737 Newton. Now, negative because it's going backward, right? The force is going in the opposite direction from where your car is moving. Now, we have done all of that. How can that help us do our work done? Now, remember, work done. So finally, we can do work done. So let's do it down here. Okay, so maybe you run out of space. So work done is force times distance. So work done by friction will be friction force by distance. So work done by friction is force of friction times distance. Okay, so we have force of friction already. Negative 4,737. How long did the car travel? 42 meters. So it's the same number. So the car moved 42 meters with friction on it. Therefore, the total work done by friction is roughly negative. You know what? It's a big number. Roughly 200,000 joules of energy. Now, every time you stop your car needs to make the energy go away. Like your car is moving, so it has energy. But every time you want to stop your car, your brake has to make that energy go away. So how does that brake do that? The brake is actually going to press against the spinning wheels of your car, the disc, and then it's going to burn up itself. So the brake is actually a device in your car that will slowly burn itself up. It's kind of like sandpaper, but for your car's wheels. And eventually, after a while, that brake does wear out and you have to replace it with a new set, which costs a lot of money. It's like $1,000 to replace all 4 sets of the brakes in your car. But you have to replace it once every, I would say like 5-6 years. If you drive more, then, more often. Okay, so when you brake, something in your car has to eat that energy. So your brake is doing that. So your brake is just a piece of metal with leather and plastic on the front. It's basically just pushing against your car to try to absorb the energy and slow it down. But eventually, just like grinding everything, right? You will if you do this with your fingers, with your hand for like an hour, the skin will come out. So the same thing works with your brick. So work done can actually be negative. So work done can be negative sometimes if the force doing work is in the negative direction compared to where you're going. So negative work done means you're removing energy from the car. Positive means you're adding energy. So it makes sense. Like, like bank account, right? Energy, if you think of energy like money, you can have positive money, which is money you put in your account. You can also have negative money, which is what happens when you spend money. So money doesn't have a direction, but if you look at your bank balance, it can be positive or negative. Okay, so now this, actually I didn't erase that one. Perfect. So copy that equation first. So this is what happened if the force and the distance is not in the same direction, you have to change the equation by a tiny bit. You have to add a cosine theta to it. This only happens if the force and the distance is not in the same direction. Now, when will that happen? This happens every time you move a suitcase. Look, I'm dragging along my little mini suitcases right now. Look at the direction of my arm. That is the force, which goes this way. But look at which way the suitcase is actually going. The suitcase is going horizontally on the ground, right? So you see, my applied force, just like that picture, is at an angle. So my applied force is at an angle, but my movement is horizontal. Just like this picture, right? So my arm is at an angle. I'm pulling the box, this way. However, even though I'm pulling the box this way, it's rolling horizontally on the ground. So every time you move a suitcase or luggage like that, you do have a situation where, it's more convenient, right? Of course, I can get very close to the ground and start pushing it, but then I'll be crouching, and that's not comfortable. So most people, if you want to move a box really heavy and it's really low, of course you can, try to lay on the ground and push it, but no one does that. It's dirty, right? Why are you laying on the ground? So we use a rope or we use a handle like this, right? And when you do that, it'll be like in this idea. So someone is pushing I'm pulling a banana box, like this with a rope, okay? So instead of actually pulling it on the ground, you stand up and then you start pulling it from the rope. So this is just a rope, okay? Now, the question said you're able to get this moving to about 11 meters. So from here to here is 11 meters. So that's your distance, 11 meters. Okay. So the tension in the rope is 90. That's your applied force. Right. So you're pulling right here. That tension is your applied force is 90 Newton. And the force makes an angle of 35 degrees. And that's it. You have everything you need in order to do this question. So you have the force, the distance, and the angle. So once you have all those three things, then you can use this equation to find out the work done. The force, the distance, and the angle. Now you will need a calculator for the angle part, even if the force part is easy. So the force is 90 Newton, the distance is 11 meter, but you definitely cannot do the cosine 35 in your head, even if you can do the first two, right? Cosine 35 degree. Don't expect yourself to do it in your head. It's okay. Take a calculator and then do it from there. So it will turn out to be 811 joules. You can check it, but it should be right. Okay. So we are only using the component of the force that is actually in the same direction as the displacement. So we're only using one component of the force. So in a sense, that is parallel to the displacement. Okay. So now that is cool. So basically, okay, so now that page is done. Okay, but this equation right here, let's talk about this even more, a little bit more, which is lifting an object, and that is on our next page. So we're just going to go into that equation a bit more. That equation actually has a special name. That equation is called potential energy. Okay, potential energy. So especially it's called gravitational potential energy. It's the potential energy of lifting up something. So potential energy means energy that you can store in something. So technically, for example, you can have chemical potential energy. So you can have chemical potential energy. So potential energy, usually we use the symbol EP, right? Potential energy. So E with a little p. So chemical potential energy, for example, can be stored in food, can be stored in batteries. So food and batteries store energy in it chemically. So when you eat food, the molecules in the food breaks down in your stomach and gives you the energy. Or when you use a battery, the battery inside has chemicals in it, usually copper and magnesium. And when you use your battery, those chemical reaction happens, and then you get energy from it. Now, you can also get potential energy from, for example, something that are elastic. For example, if you have an elastic band, so elastic potential energy is also a thing. If you have an elastic band, then or a bungee cord or a bow and arrow, that kind of thing, something that can actually bounce, or a spring, right? So those you can store energy in a object like that, right? Okay. So now, but in this class, we'll focus on one specific type, which is called gravitational potential energy. So gravitational, gravity. So gravitational potential energy. Okay, so that's the one we are going to actually focus on, which is the equation that you saw earlier on the last page. This is the energy that you can store due to an object's position in height. So an object's position in height. So, okay, now energy is the ability to do work, to do damage, right? So for example, if you pick up an object and you dropped it, it will do damage to the ground. The higher you release the object, the more damage it will do to the ground. So therefore, you can actually store energy in an object by just making it go higher. The higher the object is, the more energy it will actually store, and the more damage it can do potentially, right, when you actually do release it. Okay, so energy can always be transformed from one form to another. Okay, so energy can be converted. Okay, converted. Energy can be converted into different form, by doing work. Okay, so for example, what does the electrical fan do? It converts electrical energy into, spinning. What does a light bulb do? It converts electrical energy into light energy. What does a speaker do? It converts electrical energy into sound energy. So what does your touchscreen do? It converts, some kind of motion from your finger into electrical signal so that your phone can actually register. Therefore, basically all the machinery that you use, or all the electronic equipment that we use, is a device that converts electrical energy to something else, right? To light, sound, heat, and other things. Okay, so now the equation in here is exactly the same as the one we just wrote down on the last page, but now we have a name for it. It's called potential energy, so we no longer say work done. So potential energy, gravitational potential energy, is equal to mgh. Now remember, all energies are measured in joules. This is mass, of course, is measured in kilogram, and g is just acceleration due to gravity, so it's measured, it's 9.8 if you're on Earth, right? And height is, well, h is height, which is measured in meter, right? H in height is measured in meter. Okay, so m, so mass in here, so mass, right? So mass, which is measured in kilogram, right? G is just the acceleration, and that is, if it's 9.8 if you're on Earth, right? So 9.8 if you're on Earth, like if you're on Earth. So the question could very well put you in some other planet, so that it might not be 9.8. Just use 9.8, not negative 9.8. So when you calculate potential energy. Now, okay, so the equation is always measured from a reference point. So when you use this equation, be careful. You have to ask the person, hey, yes, I can calculate the potential energy of this object for you, but you have to tell me where am I dropping that object to. So you need a reference. So you need a reference point. Okay, so you need a reference point. That reference point is like where. So you have to ask the person, hey, where are we dropping it? So where is height equal to 0 for you? Like where's your ground for you? For example, if I ask you, hey, what is the potential energy on Yoda, right? Stuffed animal Yoda. Then you might say, well, depends, Mr. Chang. If you're thinking the ground is 0, then the potential energy is mass times 9.8 times the difference, the height between the object to the ground. But what if I dropped it to the table? Well, then, yeah, then the potential energy is mg, but then the height is only from the table to Yoda. But what if I drop it to the first floor? We are not even on the ground right now, right? We're on the second floor. Well, if you're dropping to the first floor, then it will be mass times gravity times the height between Yoda and the first floor. So you can see height is not a number that is fixed in every question. It depends on where you're actually dropping the object. Where is height equal to 0 for you? So you always have to ask the question, where? Where are we dropping it from? So now, for example, in this question, you have a textbook sitting on a table. And then, so you have a table there. The table itself is 1.2 meter tall. And you have a book like here. And then you lift the book to here, right? So someone lift the book here, which is 0.8 meters above the table. So there's a lot of distance going on. Okay, so we need to know which one is which. How much potential energy does it have if you drop it back to the table? Okay, if I'm dropping the book back to the table, then my height is going to be just 0.8, right? Because I'm dropping from where it is right now back to the table. So therefore, the potential energy, which is mgh, is going to be the mass of the book multiplied by 9.8 multiplied by the change in height. So let me just cheat a little bit because I'm running out of space over here. Let me just move that over there so I can show you the actual number. There you go. So the mass is 15 kilogram. We are on Earth, so 9.8 for the gravity, and then height is 0.8 only. Okay, so mgh, done. Usually, very easy calculations. Energy calculations are usually very easy. Just a whole bunch of multiplying and dividing. Okay, so now if you take the calculator and put all these together, you're going to get, I believe, 118 joules of potential energy. 118 joules of potential energy. Now, but then the question follows up. What if you drop it to the ground then? Oh, so that means I will take the textbook, but then instead of dropping it on the table, I'm actually dropping it to the ground. So if that's the case, let's say the table is here, right? Then I have to find out what is the height between the ground and the book. So that's going to be your height if you're dropping it to the ground. So then in that case, it's going to be a total of 2 meters because it's 0.8 meters from the table with 1.2 meter from the table to the ground. So together, I would drop like 2 meters in total, right? So that is a logical observation Then you take that and you go, well, in this case, mgh is going to be just a new h. So it's still 15, it's still on Earth, but it's no longer going to be 0.8 meter, it's now 2 meters. Yep.
What if it's like, for example,
Okay, so from the table to the ground is 1.2. From the table, from the top up to the table is 0.8. So from the top all the way to the ground is 2. So how much potential energy does the book have? That means how much potential damage it can do. Well, if you dropped it on the ground, it will do more damage than dropping it on the table. Okay, simple as that. So this equation is usually very easy to use. Okay, so final one on bow. So this one is a potential energy, but not on gravity. So this is the potential energy of a bow and arrow. So you have a bow which has a string, and then you have an arrow which you put on it like this. Now, if you know how this works, you're supposed to pull back on the, so you're supposed to pull back a little bit on the wire, like here, and then your bow is now ready to fire. So when you let it go, it will go forward, pushed by the string on the back, and it'll go really fast. So now it says in here that the force is 240 Newton. So there is like an applied force, 240 Newton, and the bow moves in a distance of 0.2 meter. So you have your distance, and you have your applied force. So the applied force come from the elastic wire itself. So that applied force is 240. Let us finish just this one. So work done. So work done can also be force multiplied by distance. So in our case, the applied force is from the elastic spring, 240 Newton, and the displacement is 0.2 of a meter. So at the end, the work done on the boat is 48 joules. Okay, right there. All right. Now, so don't worry about the bottom part. So I'm crossing it out.